Exercise 41.8. The exercise is to be solved with the assistance of the TI-Nspire CX CAS version 3.2. Consider the region bounded by the graphs of y equal to x cubed minus 20x squared plus 22x plus 600 and y equal to 3x squared minus 336. Part A. Provide a graph of the region. Part B. Provide a graphic approximation of the area of the region. Part C. Provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. Part D. Assess the correctness of parts B and C by examining for consistency between the two results. Part E. If able, obtain an exact value for the area of the region. Part A. Provide a graph of the region. Alright, in order to create a nice looking solution, I would like the first page to be a summary of everything and have all the other pages be supporting documents with detailed calculations and graphs. So starting off then with a notes page for page 1, and I can title it as Exercise 41.8 Solution Summary. Part A, we know we're going to put the graph of the region on page 2, so we can point that out here. Also, while I'm here, I think I want that very first line to be bolder, more prominent, because it is the title of this solution here. So let's go and format this text. First, let's make it bold, and let's see if we can increase the font size without forcing a wrap. That looks pretty good there. Okay, it's already rather centered. I think I'll just leave that alone as is. And let's proceed to page 2 to do our graph here. So Control Add Page, add a graph. Alright, well, the entry line is open here, ready for us. I do like to look things over for a minute here and try to anticipate some of the basic characteristics I'm looking for ahead of time, even before letting the graphics calculator do its thing, because I want to make sure that I'm not perhaps omitting something or whatever, and by anticipating what's supposed to happen ahead of time, I have an idea of what I am looking for. So for starters here, the first function I see, okay, cubic function with a positive ax cubed term, those basically fall into one of two shapes. One, like what's shown here, has just an inflection point, no relative extrema, or the other version is one that has the inflection point and a pair of relative extrema. Alright, so I'm expecting that for starters here. I'll go ahead and put in its formulation. Well, based on this little snippet, it looks like it's one of the cubic functions that's going to have the relative extrema. Okay, not going to think too much else about that just yet. Let's get this second function put in here. So tab to bring up the formula line. What are we expecting here? Okay, that's a quadratic function. That's going to have a parabola which opens upwards, having a vertical axis of symmetry. Also, with that minus 336, that's going to take the parabola y equals 3x squared and translate it down 336 units. Okay, very well. Now at least we know what to expect. Let's put it in here. Okay, well, nothing else even appears here. That's alright. We know what we're looking for. We're supposed to be seeing a parabola intersecting one of these cubic functions that has a pair of relative extrema, and until we see that, we know we have work to do. Let's see, in this case, since the action may very well go on between x is negative 10 and positive 10 or so, maybe an idea here would be to do the menu zoom fit. This will leave the x-axis untouched, but change the y-axis to whatever it takes to make the y-coordinates appear. Alright, we got that. Okay, now we start to realize that, okay, here's the red one is our parabola, the blue one is our cubic function, so it certainly looks like there's going to be more region to the right that we need to concern ourselves with. I think I'll just grab the axes, pull over. Alright, now it's in sight, and I know that there is no other bounded region sections that are missing because we've anticipated the shapes of these two functions, and we're certainly seeing all of what could be bounded with this much here. Now we want to go for the aesthetics, make this look nice and clear. Alright, well, the bounded region should be sort of filling our artist's easel here, the coordinate system, and to do that I think I sort of like this zoom box feature. Alright, now I want to have the region filling most of the coordinate system, but I also need space to put labeling, so it's a little bit of compromise there. Let's see if this will be enough for us. Now I can get the graph functions labeled with the space above. Do I have room for the intersect coordinates? I think so. Okay, I think I'll escape, put that tool away, and start to move these labels into better locations. Don't want them in the bounded region area. That's the prize area. Now something else, and that is I'm looking at these axes. I find they're rather densely scaled, and the numbers here are kind of clumsy looking, like that y-axis there. The final coordinate is 1427.72. Okay, I want to make this look crisp and clean, so let me go to the menu, the window settings, make simple numbers here, x min. Alright, let's say -8, tab, x max. Alright, 21. Right now the x-axis is 29 units. Okay, I usually just divide by 10 and make it into a natural number, so in this case maybe 3. That will be, I think, fine. Y min. Okay, well, -800. Y max. Okay, 1500. Alright, right now the y-axis is 2300 units long. I'll say every 400 units a tick mark should be fine. Not look so dense. Okay, I like this. Now, those points of intersection are important. Those belong on a graph of the region. And I am also concerned that I don't want to have a lot of decimal places recorded for these points of intersection. It makes things look clumsy. However, I want to sort of see what numbers they have here before I go change the settings on the display digits. So, okay, first let's just get these points with whatever display digits is set right now, and then change it if we don't like how it looks. So for this we can go to menu, geometry, points and lines, intersection points. Here I just need to select the two graphs I have in mind for intersecting, and all the intersection points will be displayed and computed all at once. So that one and that one. Everything appears. Now that I see these points, okay, by having hundreds, three digits, that will display without forcing it to go into scientific notation, and so I think I'll go with that. The area, okay, we may see some 4-digit numbers there, I'm not sure, but that will be okay. I think I'll keep these at 3, which means now for the menu and settings, going to the graphs and geometry settings, I'm going to float 3 and okay there, and that simplifies what we've got displayed here. Now I want to move these points so that they're not in the region or sitting on top of graph. Now I want the bounded region to be very clear, so it's time for some shading. A nice way to shade specific regions is to basically delineate with a polygon and then shade the polygon, and then remove the polygon that is temporarily used for shading. So for that, menu, geometry, shapes, polygon. Alright, here we go. Now, to shade the polygons, first need to select the polygon, context menu, and color, fill color. I'll choose yellow. This one, same thing. Okay. Now I don't want these polygons anymore. They were just here to help me shade my region. However, these polygons are useful for part B, a graphic approximation. So in light of that, I will actually store a copy of this as a future page 3 before going further with this one. So to do that, let's go with Control and expose the document, show the document pages. This one, copy it and paste it. Alright, there is our future page 3. Let's go back to our page 2 and continue to clean it up as a graph of the bounded region. So right now, those polygon line segments, I should just turn those into yellow to be part of the bounded region shading. So that's a matter of polygon and color, line color this time, and make that yellow as well. Same thing for this one. Okay, getting better. Now, all these vertices, except for the ones that happen to be coincident with points of intersection, are distracting. So, I can get rid of those by context menu, hide, and do this repeatedly. Alright, it's starting to look really nice. The last thing is, just so that someone reading this clearly knows what's going on here. I'll put some text in and point out that the bounded region is shaded yellow. So here it's a context menu, select text, and keyboard away. Okay, that looks like that's pretty much it. So we've got the bounded region graphed. We have the key function graphs labeled with their formulations. We have the key intersection points with their coordinates. We have the axes scaled and labeled, and I think it looks pretty nice. So there we are with part A all set. Part B, provide a graphic approximation of the area of the region. Here we have our polygons, which now we want them for purposes of their areas, which represent approximations to the area of the bounded region. So grab the polygon, context menu, measurement, area. Okay, I'll move this interior to this section of the region. Need to do this same thing for this polygon, measurement, area. Okay, now let's see, I had to go to scientific notation to record those. Here's where you can sort of decide, gee, should I change it to 4 floating digits here and just make those numbers, but then all these coordinates on the well, at least two of the points on the intersection points would require another decimal place if we do that, and that makes those messier. Could go either way on this. I think I'll just leave it alone. Okay, so we have times 10 to the third in each case. Those are thousands then, and we can kind of add these up, I suppose, just about mentally. Something else you could do. Why not? Here, why do something mentally when we could just do a easy way, have the Nspire do the work for us? What you could do is you could select this. There, when it's blue, it's ready for selection work. Wait a minute, I think I just want the numbers, so let me go to the end here, shift and arrow right, just getting the number, and go Control C to copy this number, and I'll go to a scratch pad, and I'll do a Control V to record that number, and then we'll do a plus, and go back and get this number. Okay, I push down the shift key and arrow over to select just the number part. I don't need that U squared is not what I need for this right now. Then I can do a Control C, can return back to the scratch pad, and Control V, and add those two together. Okay, so for graphic approximations, I find recording more than 2 digits is a little bit too much. It's just something that's kind of visually an approximate, so we'll call this 12,000 for the purposes of the approximation here to the nearest 1,000. And let's escape this scratch pad and go back here, and we can make a text statement right on the graph would be good, and then we can record it on the notes page, the solution summary as well. So for here, text, and now I want to go to my solution summary page and make note of the same thing, maybe describing how we have arrived at this part B. We could say that an approximation of the area can be obtained by the areas of approximating polygons. The resulting approximation is 12,000 square units. And we should refer to the person who wants to see details to this to its page, which is page 3. All right. Part C. Provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. To use calculus to find the area of the region, let's take a look at some slices. Specifically, let's try thin vertical rectangle slices and see if those look like a good strategy. Okay, so can we write an informal formulation of the area of one of these thin vertical rectangles? I think so, but there is one little problem, right? And that's that we have in mind the length of any rectangle as being the upper y minus lower y coordinate, but watch what happens to the upper y as we sort of travel across the vertical rectangles. The upper y initially is determined by the blue F1 graph y coordinate, but then things change midway through. The upper y coordinate is determined by the red graph y coordinate. Okay, no problem for us. We've been in this predicament. When the curves crisscross, as we're doing here, we have been able to formulate the area of a thin vertical rectangle as being the absolute value of the difference of y coordinates times a width of dx. So let's do that here. So by visualizing, we've got ourselves a strategy for computing the area using calculus. Let's describe to the person reading our solution the basic idea here, and that would be to say that the area can be calculated using calculus. with a definite integral which sums thin vertical rectangles, and we should point out that we will store the limits of integration in variables a1a and c1a. Okay, now we need to get those limits of integration stored. Let's go back to that graph there, and let's take this context menu, store. Alright, traditional left-hand limit of integration is given the name A, but it's the TI-Nspire. We don't want to use single letter names, so now that makes A1. And since this is actually a decimal approximation of A, we'll call it A1A, and then hit enter. Just in case something comes up, I can't resist storing this one, intermediate point of intersection, in a variable right now. Okay, I'm going to store this in B1A, although it may not ever be used, just to have it while we're doing this. Here is the third one, so this is why the letter C, A, B, C, and let's go ahead and store this like we said, C1A, enter. Okay, returning to the notes page to now perform that definite integral calculation. Menu, calculations, calculus, integral. Okay, lower limit A1A, tab, upper limit C1A, tab, integrand, absolute value of y sub 2 minus y sub 1, or actually in our case f2 of x minus f1 of x. There we are, and let's make this with that little triangle to be a equal sign here. Alright, we'll make it, since we're actually having a decimal approximation distinction, we'll make it an approximately equals to sign. Let's see, we have here, it's recorded 6 digits. I thought we recorded 5 floating digits for our document. Let's go fix that. Alright, so here with the documents, settings, okay, float 5, okay, alright, there we are. Now that is almost complete, just maybe adding on here the square units idea here. Okay. Part D. Assess the correctness of parts B and C by examining for consistency between the two results. Well, let's look back at that graphic approximation. We found it was 12,000 square units on a graphic approximation. Okay, let's record that. Now let's look back at that calculus calculation. It was about 12,300. Oh, let's record what it is with 5 digits there. The calculus calculation was 12,314. Oh, this looks very good. Okay, well, let's see. The difference is about 300, right? 300. Well, if it was 10%, that's 1,200. If it was 1%, 120. So, okay, 3% is no exaggeration. So we're able to say that these two results are within 3% of each other and thus consistent. Therefore, the solutions of parts B and C are likely correct. Okay, that's great to see that. Part E. If able, obtain an exact value for the area of the region. So for exact calculation, we have two hurdles to cross. Let's try them one at a time. And so here we've got our part E. And we can point out to the reader that first we must be able to solve exact limits of integration. Let's actually go and try this on another page here and see if we can get something going. Now for exact work, you don't want to be on a graphics application. You want to be on a calculator application. So let's get a page 4 up and running here with a calculator application. And those limits of integration come as a result of solving f1 of x equal to f2 of x. We want the x's. Let's see what happens. So solve parentheses f1 of x equals to f2 of x for x. Cross your fingers and hit enter. Okay, great. We've got all three of those x coordinates of points of intersection. We probably will need all three of them. Now that they're sitting here before us, let's go ahead and store them into some variables. So I will go back up here and okay, starting here, shift key, arrow to the right to select this number. Now remember, when the Nspire solves an equation like it did here for x, these are in ascending order, so they're going left to right. So this is A1. Okay, so by the way, now I'll push enter to bring it down to this line here, and now I go with the control store to and A, because it's on the left, 1 because we don't want to use single letters, and now I'm not going to put that suffix A on it anymore because this is not approximate, this is an exact limit of integration, and enter. Okay, and I repeat this with the other two numbers. Okay, so we successfully got the three limits of integration that we may very well need here. So let's go back to that notes page and point that out. And we should point out to the person reading this document that we have stored these limits of integration into variables A1, B1, and C1. Okay, the second issue is, will the Nspire's definite integral function provide an exact result for us? Well, here's what we did last time in part C when we just had to get a decimal approximation. We used the sum of thin vertical rectangles, and we used the idea that the length of these rectangles would be the absolute value of f2 of x minus f1 of x. But you know what? We can't do that anymore. And the reason is that by using absolute value in an integrand, the Nspire automatically goes into decimal approximation mode and abandons the idea of giving you exact results. So what can we do? Okay, well, we can still formulate the areas of these thin vertical rectangles, but since these two curves crisscross, we're going to need two separate formulations, and therefore we're going to need the sum of two definite integrals. On the left-hand portion, these rectangles have a length we could describe as being the blue y-coordinate minus the red y-coordinate, or algebraically, f1 of x minus f2 of x. Then, moving to the right subregion, those vertical rectangles have a length of the red y coordinate minus the blue y coordinate, or algebraically, the f2 of x minus f1 of x. All the rectangles have a width of dx. What about the limits of integration? Okay, well, the left rectangles start off at the leftmost point of intersection, and the little dx's march across until they come to the middle point of intersection. Thereafter, the second integral comes into play with its dx going from the middle x coordinate of intersection to the far right point's x coordinate of intersection. Okay, we're ready to formulate. So, menu, calculation, calculus, integral. Okay, A1, tab to B1, tab F1 of x minus F2 of x, tab dx for the width of each rectangle. Okay, plus okay, now this one goes from B1 tab to C1 tab. Alright, now these inverted rectangles have a length of f2 of x minus f1 of x dx. Let's see if we can get exact out of this. Enter. Okay. Got something there. Looks like an exact result. First, let's fix up this box here a little bit. Let's make that little arrow an equal to sign. This is exact work. And maybe here we could also tack on the square units. Thus, we have obtained an exact area calculation. Now, before we go further, wait a minute. Let's make sure this is consistent with our part C, the decimal approximation. Otherwise, we actually have a problem here. So, this number here, Shift key, arrow to select it, Control C to copy it, down here, Control V to paste it. And now I'm going to go to the menu, and as an action, I'm going to have it approximated. Okay, very good. And that is the same as part C. By the way, let me change that arrow so that it is an about equals to sign. Okay, good solid solution. Really convincing.